Right. Well, we'll begin at the beginning anyway. All right. So backing up, we're gonna learn how to multiply vectors here. There's many different ways to involve vectors in the process of multiplication, many, or at least three. One of them we already know, which is we already know how to multiply a vector by a scalar. When we do that, we're taking an arrow and stretching it or shrinking it, and the result of that process is we still find an arrow. That is, multiply a vector by a number, you just get a vector of a different size. We already know how to do that, but it's actually a very important thing to know how to do because it's one of the couple of things we ever do with vectors at all. One is we stretch or shrink them. That a vector is an arrow. So sometimes we stretch and shrink the arrow, and that creates a vector of a different size. Another thing we do is we put the arrow with other arrows tip to tail, and we think that means, and that performs vector addition. That's like all we know how to do with arrows so far. But the idea is that doing things to arrows on the page literally computes quantities for us about space. Like, they're not just rough pictures. If you treat arrows seriously, like in free body diagrams, then they actually are a computational tool just without buttons. So, all right, so let's be precise. Let's use the tool and be precise about notation. If you have two vector quantities in space represented by two arrows like A and B, each one has its own magnitude and its own direction, which together uniquely specify that quantity. From now on, if I either put what look like double absolute value signs around a vector, or I just leave all the vector notation out completely, either way, that explicitly refers to the size of some vector. Like we have a vector A. Normally, if we're in vector, we're gonna be precise about that by putting a little arrow over A, making sure we know it's a vector. But if we're just talking about its size, then we write it either of those two ways in blue. That's like the pure size of A. Well, then this is the key step, just as a piece of notation, but a really powerful one that it's good to get straight from the start. If we can define, this is where I need my pen. We can define, I really don't know how long. We can define a symbol, a new piece of notation, and it is A with a caret on top of it. No. Okay, good. What I'm saying right now is here and all for all time, this symbol means this. It's like almost seems dumb to say, but it's like hugely not dumb. We're going to define A hat to be, A with a caret on top of it to be some vector A, whatever, any vector A divided by its own length. Now remember, we know what it means to multiply or divide a vector by a number. Like if you multiply a vector by a number, you stretch it. You stretch the arrow by that factor. Like the arrow is, the vector is an arrow and a number is a pure size. So here what we're saying is, imagine taking some vector and shrinking it, dividing that arrow by its own size. So what you would get is, if this was the original A and you divide it by its own size, you get a vector that would point in the same direction as A, but would be a lot smaller. In fact, how many times smaller would it be? It would be necessarily length. Well, maybe you could, its length would be, I don't know if anybody wants to say, if you take a vector and you divide by its own length, so it's like you take something that is 4 meters pointing to the northeast and you divide it by 4, what you're always going to get is a vector of length 1, like 1, whatever units we're in. If we're measuring meters, 1 meter. If we're talking about force vectors, then 1 Newton. But this thing, A hat, A with the caret on top of it, is what then we call the unit vector for A. I'm gonna write that. Okay, so there's some vector called A. We know it's a vector because it's got an arrow like in its notation. A with a caret on top is going to be known as the unit vector for A. Like it's a separate vector, it's its own vector, but its purpose in life is to be a vector that points in the direction that A does. A points wherever it does. And A with a caret on top is our piece of notation or our way of signifying the direction of the original vector A. But that's all it signifies. It's meant to purely and only signify direction. It doesn't signify anything about size. It always, by definition, will have a size of 1. So it's not getting involved in the discussion of size. And that's all on purpose, so that even we define it this way, in the end, the purpose of it is to be able to then think of that original A vector as a simple product of two simple pieces. Like from now on, or of two pure ingredients, you could say. Any random vector A is an arrow that has a size of A, like A is a number that tells us how long this vector is, and it points in a direction known as A. A with the caret on top is purely pointing out the direction, and then so A with a caret on top is some arrow pointing somewhere. That gets us let me start again. Why I keep stumbling is, okay, this caret, the caret is so annoying. The caret is in physics itself, that piece of notation, the caret, we don't call it a caret. We call it a hat because we are so fashionable and cool. We always call that a hat. So when we're reading, if I'm reading this in a book or something and I see a arrow, a hat, like not like, oh, look, there's a hat on that guy's head, but like this is known from now on as a hat, which is the dumbest name ever, but that's what it is. So it allows me from now on to think, okay, a hat is a designator of just the direction of A. A is the letter A is the pure size. So the way I think of the vector A from now on is someone took a random little vector of size 1 and they pointed it off in a certain direction. And they said, we're going to call that direction A from now on. And I said, great. And they said, so now, and they stretched out that arrow to a certain size and they said, and now we're A size pointing in A direction. Here you go. That's your arrow. Okay. So from now on, a hat is the unit vector for A. If we have any two random vectors, then A and B, each one is thought of as a simple multiplication, a simple product of its size and direction. And like they differ in size, they're random, and they differ in direction. And the way in which they do each is like how they're related to each other in vector space. So I could draw them tail to show how they differ, their difference, and call that angle between them theta. Draw them tail to tail because I'm looking at their difference. If I put them tip to tail, I'd be adding them. But all right, so now we've got two vectors, and but if I want to look at them in relation to each other, these two vectors now, well, one thing I know, the only thing I know how to do is add them. I'm not sure that's what I want to do, but remember what it means to add vectors is to put arrows tip to tail, right? When you put arrows tip to tail, each arrow is itself a vector. A vector is always a size times a direction. So A itself, I'm going to break it up now. Like in physics 203, we realized if you want to put two vectors tip to tail and add them, you can make that picture, but to see how the numbers work out in that picture, you could break each vector apart into a smaller sum. And the reason for doing that is we noticed, like in lab 3 in 203, that how much you walk to the north can add up with how much you walk to the south. So you can walk 3 meters north and then walk 3 meters south, and they actually do the same thing as they would on a number line, and you get 3 plus -3, and you end up at 0. But north doesn't add to west that way. North and south affect each other. East and west affect each other. but the two axes function purely independently. So what we used to do in physics 203 is break up each vector into like a smaller sum of simple products, right? So here we have vector A is actually the sum of a small vector in the x direction plus a small vector in the y direction, and the same thing with B. And the fact that they had axes in common meant that we could add the vector. You can only add, in other words, vectors that are parallel with each other. So as long as you agree on axes in advance that all vectors can equally talk about, then you can add them. So we're going to use the x, y, and z axis so much. I mean, they're the axes that are common to everybody, that we give them special names. We don't want to keep seeing the x and y and z over and over again either. So from now on, we're going to use I, this is the point of this page, we're going to use I, j, and k instead of x, y, and z. Like some books will use both. You'll see both, but the more common is I, j, and k to actually stand for the unit vector that points along each of those axes. Remember, you can have a unit vector for any axis, like a hat is the vector of size 1 that points in the a direction. But x, y, and z are such sort of common special directions to us that, okay, we give those their own special unit vectors, I, j, and k. If we define vectors, if we start looking at vectors this way as a simple product, like what I'm saying is that the way to think of vectors is vectors are arrows. Vectors are arrows that can be moved around the page without changing their value, the information that they carry. So if you have a given arrow, you can stretch it or shrink it, and that will change that arrow into another arrow. If you place two arrows next to each other, tip to tail, you can thereby add them. The result you'll get can only be understood on paper if you recognize that addition as it works in the number line only applies to one number line at a time. So I'm going to start looking at multiplication now. I'm going to say, what does it mean to multiply two vectors? Well, we already this whole time have been tacitly believing that you could multiply a vector by a scalar, i.e. stretch the arrow, and that was an okay thing to do, but it always resulted in a vector. We already know that if you multiply a vector by a scalar, that will result in a vector. So it raises the question, if you multiply a vector by another vector, is that going to make a scalar or a vector? Well, actually, it can make whichever one we want as long as we use the right tool. There's a tool for each. This thing that I'm doing right here on this page is I'm defining what would be the simplest, most straightforward procedure for multiplication that would honor all of what we ever believed multiplication to be, but would be of a sort that would produce an answer that was purely scalar. Like, what does it mean to multiply two vectors? What does it mean to find a product of two vectors that itself is unconcerned with direction or doesn't convey anything about direction? Well, I don't know offhand, but I know this, like whatever that procedure would be, it would have to look exactly like regular old multiplication if the two vectors involved happen to be purely parallel. Because whatever this procedure is, if I apply it to two vectors that are purely parallel, I'm in effect applying it to two numbers on the number line, right? Like if two vectors are parallel, they lie along the same line. So then whatever it meant that whatever happiness it gave them to be vectors, like, is now irrelevant. They are as if I was multiplying two numbers on the line. So it better produce the answer that I would get under those circumstances. And presumably the answer has to differ more and more the more these two vectors don't lie along the same axis, right? So we want, if we want a scalar product of two vectors, we're going to want it to produce a number that more and more resembles regular old multiplication, the more and more parallel these two vectors are. So this, I wish I could write this down. The scalar product, I'm trying to say, whatever it is a measurement of the extent to which two big vectors are directionally similar. It's a measurement of how aligned they are. The dot product is a measurement of alignment. So what it is this, I mean, on the page right here, A vector dot with B vector gives you a pure number whose size is the size of A times the size of B times the cosine of the angle between them. It's like the simplest thing it could be. It's just like, yeah, regular, just multiply the size of each one, but then throw in a percentage factor. It's like a scaling factor of how related, though, how parallel those two numbers were. If they were perfectly parallel, the cosine of 0 is 1, you're going to get 100% of your good old expected answer. The more they differ with each other, the less you're going to get that. So you're measuring the extent to which they're parallel. So, okay, I'm going to pause here. And most people, look, I saw your homeworks, and I think you know a lot. Most people are maybe most people have a grasp, but a tentative grasp on the dot product. Where it usually tends to fall apart for people, because it is much more complicated, is the cross product. That's where probably most of you want to see more of what I have to say. Or like, whether you want to or not, like the cross product is where, well, a lot of errors occurred. But the best way to understand the only way to understand the cross product is to base it on a precise understanding of the dot product. So to do that, this whole talk that I'm saying so far, I've known that most of you probably feel some okay comfort with the dot product, but you may never have used this IJK stuff before. That may well be for a lot of you, that you do basically get the dot product. You want me to get onto the cross product or get onto something, but you've never seen these unit vectors before. But since you can get answers with the dot product, you may well be thinking, well, they're just like annoying. I'll figure them out later. I don't need them for right now. That's totally what I thought forever, and it completely slowed me down. Like, the truth is, let's try to get these unit vectors now in the easy case of the dot product, because they are the only way to understand anything that's coming, such as a cross product. So what I'm going to ask everybody to do is apply this upside down board. Now apply, I mean, you can look back at this, at screenshots, I guess, or something, but I want you guys to tell me what's the dot product of I hat with itself, and figure out also, please, the dot product of I hat with J hat. And I am looking for a real answer, not like a concept or a general answer. And I'm looking for a number, as a matter of fact, and you can get it. You have all the information. So if I could just get a quick like show of electronic hand or something, just if you, the question I'm asking that I want to, like I said, also distribute it. What I want everybody to do is please get, I know the board's now frozenly upside down, but I want you to get the product, the dot product of I hat with I hat as defined by me, I hat as defined in like today's lecture, and then get the dot product of I hat with J hat. I'm going to try to write this down again, but my whole board is obviously doing its own thing. And I'm also definitely going to turn off the board while I'm asking you to do this, because I'm going to try to reboot it. So I hat dot I hat and I hat dot J hat. That's the questions, you guys. Can I get some recognition that you know what I'm asking you to do? Thank you. That's awesome. Thank you very much. Thank you. Oh, I love it. That's, you know, I'll tell you, it's a sip of water in a desert. It's like a fish without a bicycle. Okay. Yeah. So, and you can talk, and I'm just sitting here trying to fix this whiteboard. Okay, if this is like our XYZ coordinate system. Okay, there's like a vector of unit 1 length, like this vector here. Is supposed to be pretty short. It's supposed to have a length of 1. And it's supposed to, by definition, yeah, like lie right along the x-axis. And then there's another one like that on the y-axis and another one on the z-axis. Each one has a length of 1, and they point along that special axis. This one along the x-axis happens to be called I. It could have just been called X with a hat over it, but it's called I with a hat. And I'm literally asking, what is it? What's the what happens if you take that vector and do the dot product with the very same vector? So we're talking about by the definition, that means take the length of vector I, whatever the length is, times the length of vector I again, times the cosine of the angle between them. And that factor is there like as a percentage factor to take into account how parallel these two vectors are. The more parallel they are, the more that big factor will be. So what is the length? So I'm just going to plug in now. What is the length? Someone besides Brochet, what's the length of I hat? Or actually, I guess Brochet did basically say this. Yeah, I mean, I think she's definitely saying that the length of each one is 1. And we're not like supposing that. That is by definition of I hat. It has a length of 1. So it's 1 times 1 times the cosine of 0, which is not coincidentally also 1, so as to give 100% reckoning to fully parallel vectors like this. So yeah, so the answer is 1, okay? The answer to the dot product, in other words, of any unit vector with itself equals the number 1. The dot product always gives you a number, could be a negative number, could be 0, but in this case, it's 1. The dot product of I and j, like what is I dot j? Someone just chat maybe the answer, I dot j. Yes, awesome. Yes, totally 0. All right. So I dot, now, okay, that's the, but why this is useful, why this will help us with the cross product, which is the goal here. Understand the dot product. Remember, I defined it to be AB cosine theta, but if that's the definition, okay, this is where we were. If A vector dot B vector equals a pure number, AB cos theta, like it just gets this number, oh, well then I guess, oh, well the number 1, that's enough right there to go over the answers to some of this. I almost forgot. Like the ranking stuff, the first problem on the math methods, ranking, you were told that, you were given this picture and told that all the vectors were the same size, so they differed only in direction. And then the different combinations you're given, the entire question then is, even if you don't know the precise amount by which they differ in direction, the question each time is how parallel or not are they? So like the more parallel two vectors were in a given choice, the bigger their dot product was, because their sizes were assumed to be equal. So the answer is, and I think most people got this right, was A dot B, then B dot C, then A C, then A dot D, from greatest to lowest. I think most of you got that right, so I'm just gonna keep going. Now the cross product, okay. Well, actually, I need to pause before. Well, the cross product is, just as you would expect in a way, the flip side, it's not taking into account cosine, it's based on sine, because the cross product is going to be the other choice, the way of multiplying two vectors that will take into account their directional difference and give us an answer that has direction. Like the cross product is a directional measurement of directional relationship. So the more perpendicular two vectors are, the more of a cross product they'll give. That's definitely, and so again, like it'll be the size of one times the size of the other, but then times the sine of theta, which gets bigger and bigger as you get closer and closer to total perpendicularity. So I'm going to pause there and say, from that, remember, like one vector crossed with another will produce a vector, which will be, you know, that much greater if those two were that much more perpendicular. But it also, the vector itself will have to point perpendicularly to both of the original vectors, if you think about it, in the same way that the two original vectors have to be somewhat perpendicular to be crossed at all, or to have a cross product. And the more perpendicular they are, the more of a cross product they make. Well, the cross product itself has to be perpendicular to each of them, because the direction of the cross product is indicating something about their directional and size relationship. And it needs to account for each one of the original vectors with equal weight, if it's to be the operation we think it is. Like, whatever you do when you multiply two numbers together, or whatever you do when you add them together, you do to both of them in the same way. It's not like 2 squared plus 3 or something like that. So this arrow that we call the cross product of two other arrows, if it starts being too similar in direction to one of the arrows than it is to the, excuse me, if it was more similar in direction to one of the original arrows than the other, it would seem somehow to indicate like that one of the original arrows was accounted for in a greater way, like was given more weight in the relationship than the other. And that's wrong. So the final answer vector should have a direction that's equally close or far directionally from each of the original. And the only way that can be true, since it can't be parallel to both ever, it will be perpendicular to both. That's the one thing it could always be equally distributed, is it could be completely directionally askew from each one of them, i.e. by being perpendicular to the plane in which the vectors were drawn. So the cross product is a vector whose magnitude is given by this, right? Like, I have to put those lines. The magnitude of the cross product is going to be size of one vector times size of the other times the sine of the angle between them. And the direction of that vector will be perpendicular to the plane in which that was drawn. There's a way for me to not have to say that in English, but I'm not going to yet. But now to find out exactly how big that vector is, again, I have to pause. Let's look, I want to show something about the dot product. Be really careful with it. If you do the dot product component, oh yeah. Where'd it go? Yeah, remember this. Okay, yeah. Remember, each vector originally was its own sum of components. When I dot two vectors, I dot those two entire binomials with each other. Like when i.e. the dot product of A and B is actually that full quantity, this full quantity dotted with this full quantity. They're two binomials. So if multiplication is still multiplication, if it's distributive and commutative and all of that, then I'm going to do this term by term, like FOIL, right? Like first, outer, inner. So the dot product of A with B will be this list of 4 terms. Oh, I should write this. Sorry. Oh my God, sorry. Okay, if I'm going term by term, that first term is AX I hat dot BX I hat, like two vector. Remember, AX, BX, etc. are all just numbers. Anything without a vector symbol or caret is a number, and anything with a vector symbol or a caret is a direction. So this is just like, so A dot B is AX I hat dot bx I hat, like it's equivalent to two other vectors being dotted together as the first item in the list. Well, okay, that's the same thing as that's the same thing as and we said that I dot I is equal to 1. So that's the same thing as this. In other words, the first term, if I'm fully being careful about what the dot product is and fully writing it out term by term, the first term will be just this number, ax bx. Okay, and that's good that it's just a number because our final answer is supposed to be just a number. But that was the first term. The second term looked like this. That was the second of 4 terms, just foiling it out. And that is ax by times I hat dot j hat. But I hat dot j hat we said was 0, right? So this whole thing crosses out, and there's 2 more terms to go. The same pattern of 2 things happens, and we end up getting like all the unlike terms cancel out, of course. So in the end, a dot b dot in the end, you could say equals ab cosine theta. Always it does, but with the unit vector notation, you can always say that, and that's always true. But from that, we can also equally say from this unit vector notation that a dot product is just the sum of like components. The dot product is just the sum of like components, all the other ones dropping out. That's just a notational way of saying what you use when you originally played with vectors in Lab 3. You can only add or subtract things along the same axis. So to make the cross product, which is the big thing that we need and which is more complicated, to make the cross product and understand it, I'm going to do the exact same process. I'm going to say, okay, cross product between 2 vectors is a vector whose length should be the length given by length of the first times length of the second times sine of the angle between them, and whose direction should be perpendicular to both. But it's not going to be the sum of like components, because that's the dot product, and the length is not going to be the sum of unlike components, because that doesn't make any sense. You can't sum those. So what is it? We're going to do it term by term. I'm going to give it to you possibly too. If we do it out term by term, it's this right here. Yeah, we're going to do it term by term, so we have to be really careful. So I'm doing the cross product of, and this part, again, even if you sort of got question 2 on the homework right, or sort of felt okay with it, this part I don't think you would have seen before. The cross product of A and B is the cross product of the full vector A with the full vector B, written all out in components. And by the way, now I'm just, at this point in my life, I'm deciding we both can and must deal with the 3-dimensionality of space. Like I'm going to start incorporating the 3rd axis into my thoughts, because it's time. So I'm going to FOIL these out term by term, just like we did with the dot product. And with the dot product, we sort of got something I think that we would expect. But going term by term, like the first one is AXI hat cross with BXI hat, right? And then the next term would be the next term would be AXI hat crossed with BY j hat. No, yeah, exactly, et cetera, et cetera. So let's look term by term, like the first term here. I know the board is catching up with me right now, but all right. So all those terms, we're going to look at the first term. Yeah, here we go. Just like before, it's the numbers times the cross of the vectors, but I cross with I is always 0 because it's parallel with itself. And I should have asked, I should have actually asked you, in fact, I will ask you now, even before this goes on, whether you already figured it out or you saw this coming, or you just figuring it out from looking at the board. I neglected to ask you guys as an exercise, what is I cross I hat? That's the question I want to ask. What is, to everybody right now, what is yeah, good. We're actually totally still good on time. So I do want, please, everybody to pause wherever you are. This is the clearest I can be visually for the moment, and it is driving me crazy that I can't use that pen. But I want I'm looking for specific answers. It's not an arbitrary exercise. There are real answers to get for each one of these questions, and in fact, I'll even tell you that I believe it's 3 different answers. So I'll give you a moment. You could talk, et cetera, but that's what I want for right now for the cross. And we are using the definitions from today of I, J, and K, and of like, so you're looking for vectors here. The magnitude of each one will be a b sine theta, and the direction of each one will be perpendicular to the other two. Have at it. I'm still. All right. 20 minutes left this phone. Any thought, does anybody want to raise any thoughts on these? This is the question of the moment. Is I cross I, J cross J, I cross I cross J, and J cross K. Any thoughts or hopes, dreams, aspirations, favorite variety of platypus, Bueller? Do they just electronic hand if you know what the question is? For I cross I, remember that I dot I was 1 and I dot J was like 0. So if following the pattern or whatnot, it would be very reasonable and common for people to guess that I cross itself is not going to be 1 like before. It's going to be the opposite. I cross with itself, people usually often guess that it's going to be 0, and they're totally right. And it is 0, which is great. I might technically say that it's the 0 vector or the vector 0, but whatever, it's 0. Now, if I do I cross J, this is where a lot of people who are following and with the program would maybe then surmise, okay, that's going to be 1, just like the I dot I was 1. Well, you're right if you say that in a way, but you're not done. Like, the answer to I cross J is not actually 1. It's just that 1 is an answer, but to a different question. 1 is the answer to the question, how big is the vector that is the answer to I cross J? In other words, remember, when you cross product of 2 vectors is deliberately and by essence a product that results in a vector. So the size of this vector that we're going to get here sure is as big as it could be. And that is 1 times 1, it is 1, but that's just its size. Like, in what direction does it point? In fact, having said all that, I'm going to ask you guys, I'm telling you the answer to this is not 0, it's not 1, but it is a vector that has a size of 1. So what is the answer to this? What? We want the size. We want the vector. Do you know any vector whose size is 1? Right? You know, the truth is, I wouldn't be approximating that either. Well, what I'm going to say is, I know some vectors that have a size of 1. I hat has a size of 1. J hat has a size of 1. K hat, they're all defined to have a size of 1. Which one's the answer here? Well, the answer to the cross product of I with J has to be a vector that is perpendicular to both I and J, like perpendicular to the plane, and that is K. Okay, so similarly, like J cross K will give me the vector I. J cross, sorry, I did it again. I cross K. Any thoughts on that? Well, if I cross J equals K, I'm just going to say, I cross J produces a vector perpendicular to both I and J. The only vector that's perpendicular to both is K. That's what I cross J does. And J cross K produces the same vector. And the same kind of answer. And K cross I similarly produces the one vector perpendicular to both of them. But just note, I guess I just want to say, I'll just keep going. With those definitions, with that in mind, to actually get a cross product, to actually figure out what it means, what its magnitude is, and direction in terms of components, like we did for the dot product, we do it piece by piece. Like this. Like I'm going to do these. Now this is where I was. A cross B. If we write each out fully as a big three-dimensional vector, as a big list of 3 different components. If I'm crossing those 2 vectors, I'm going to do. I'm going to multiplied term by term by term. I'll have 9 terms if we're in 3-dimensional space. And I'm going to see what happens if I go term by term. Here's the first one is like ax I hat cross bx I hat. Okay, that's the first one. That's these. Well, I hat cross I hat is 0. So that first term is going to drop out. But then the next term is like ax I hat cross by j hat right here. That's the same as so that's ax bx times I hat cross j hat. These are supposed to be, these are subscripts. This is why they actually made up those names I, J, K for the X, Y, and Z axes, so they didn't get confused with these. But these are subscripts. So we have this one term. This is the second out of 9 terms that I'm looking at here. Well, I cross J, we said, is equal to K. So this one term, this is a vector here. It has a size, which is the size of the X component of our first original vector times the Y component of the original vector, of the other original vector. Like this whole thing here is just a pure number, it's a size, times K hat, meaning, okay, this first term is giving us a little vector that points in the K direction, that points not perpendicular to the plane of the original 2 vectors, but perpendicular to the XY plane. This is a term, and it has a length of ax by. That's the first term. Now I'm going to go term by term, but I'm not, because we're going to. But if there's 9 terms to do out, and please stop me if you don't see this, but I'm just foiling out all 9 terms. The first one canceled out to 0. This one did not cancel out to 0. It gives me a little vector pointing in a particular direction, or I should say it gives me a vector component. Like this is a number, so this is a component. And specifically, this is a z component of our final vector. Our final vector will point somewhat along the x, somewhat along the y, and somewhat along the z. And this is how much it points in the z. But so far, like I might get another term that has, so there's 7 terms to go. If I get more than one term that is like, if I get more than one that has a K in it, I'll collect those like terms, et cetera, and get a grand final answer. Let's assume I've done that. Well, actually, oh yeah, well here it is, right? So if you go term by term, this is what you get in the end. This is an answer. I mean, this you definitely want to write down or know, even if you did the homework to some extent without knowing this. This is not just like a random example. This is the point that a cross product of between 2 vectors A and B, where each one is looked at as a sum of 3 components, ends up producing a vector that has possible components along all 3 axes of space, right? I mean, it's going to have to point purely perpendicularly to the original 2 vectors, but they could be pointing anywhere. So you get a final vector that has 3 components, points some amount in x, some amount in the j, some amount in the y, and some amount in the z. How much? Well, this much, this much, this much. They look crazy, but what do they really amount to? It basically says that, oh yeah, by the time we got to term number, like this was like term number 2 from the first times term number, like this is when we're term 3. This is when we multiply, this is when we were multiplying it's basically saying that we got two answers that ended up pointing in the y direction, so we collected them together. One had a negative sign. We got two answers that pointed in the j direction. One had a negative sign. We collected them together, and then see this pattern once we collect. This is the answer for the cross product. It's a crazy looking beast. It's probably the biggest, like, as a piece of thing to know. If you're wondering, do I have to memorize that or what? Like, you totally end up memorizing it. Believe it, if you do physics at all, you get used to it. But at first, there's no point in trying to memorize it, but it is a pattern if you look at it. The summary is this: the dot product will always produce that, and that is always equivalent to assume that we're like in three-dimensional space, okay? That any two vectors in that space, well, they'll necessarily form a plane, those two vectors, and to dot product them is to take the product of their sizes times the cosine of the angle between them, which always will be 1. But that's equivalent if you want to think about it in terms of components, which I do want you to, because remember, only like components can add. We've always been saying. Then with the dot product is the sum of the like components of the two vectors. The product of the x components plus the product of the y components plus the product of the z components, and that's all a pure number. So these two are equivalent for the dot product. They both mean the same thing as each other, but they're useful in different circumstances. And the similar takeaway for the cross product. Oh, and this is, sorry. So this is all about alignment, about parallelism. The dot product is all about reducing everything to the number line. Pure sizes. But the cross product is the opposite. The cross product is all about perpendicularity, about carrying directional information. So it's a vector whose size will always be this size. The answers Right. Okay. So just very quickly, when we're just doing the ranking task for the vector, for the cross product, it's, as you all did get, just the more perpendicular two vectors were, the bigger the cross product was. So that was the ranking. Most of you were right about that. Then super quickly, if we were told that the length of each vector was 3, and we wanted the cross product, or we wanted a bunch of these different computations, dot products and cross products. I'm going to very fast, but clearly say these answers right now, because this is where everybody kind of fell apart a little. A dot F, okay, yeah, that you got two vectors that are anti-parallel, so to speak, 180 degrees apart from each other, like the cosine of 180 is -1. So as you might expect, so the dot product of A and F is 3 times that -1, you get -9. Most people, I think, were good on that, actually. But then A dot D, they're purely perpendicular, so their dot product is 0, okay? Then C was what's A cross F? What is the answer to A cross F? I have to be careful now. This is going to be a vector. I have to get a magnitude and I have to get a direction for it. First, the magnitude, you could do the easy way without all those components, just AF sine theta. So it's 2 times 3 times 0. Oh, okay. So in this case, since they were perpendicular, the magnitude vanishes. So my hard work is done, but I'm preparing. I have to know that whenever I get a cross product, there's going to be some direction that comes in. So A cross D is, the magnitude is 3 times the sine of 90 degrees, which is 1, so I get 9. But now it must be 9 units of length. It needs to be a vector of 9 units of length pointing perpendicular to those original two vectors, i.e. pointing perpendicular to the page in which those directions were drawn. A lot of people did know this and say it, which was great. And people that did know this, yeah, it rocked a lot. But now but perpendicular to the page now is two possibilities, in and out. It's actually not random once anybody's made any coordinate system decision. If we're crossing this vector with this vector, and let's assume that the page has an XY axis such that I hat unit vector points to the right and J hat points up. So like negative J hat points down, etc. Then we are here crossing, do the right hand rule, we're crossing I with J. Sorry, is that right? Which one? Yeah, so yeah, we're crossing I with negative J. I'm going from there, crossing with that. So the answer points along my thumb, specifically points out of the page, you could say, as opposed to in it, and or you could put it as unit vector K. So the answer to D has to have a direction, and the mathematical way to say that direction is to use unit vectors. So it's 9K hat is the answer to D. E, it's going to go the other way. It's F cross, or did I just, yeah. E goes the other way. It's F cross D. So same angle, same size things, but now we're going back the other way. So we get negative 9K hat. Then the next two answers were 9 and 0, a dot product and a vanishing cross product. If you really get that, then yeah, well, here you could just glance for a second. I mean, these are the answers to the rest. Again, it's all posts and stuff. We mostly got positive numbers here. These are all dot products, so they all are just pure numbers. But then these were the, so sometimes you get negatives, but anytime it's a cross product, we have to see vector symbols in the answer. I'm not going to start the gravity right now, but if you want to, again, everything that's in this crazy thing that didn't work today, these pages, and even if, again, this is all a PDF that you got last night. I'm going to try to make it better. But so the rest of the answers, if you're interested in the gravity and stuff, are here. I know this has been unusually, about the exam, this is what I'm just going to say right now. Tomorrow, I will post the practice exam, the real. There is already hopefully a practice exam in your box from yesterday, but I'll post the official accurate one tomorrow. Not with answers, maybe, not quite, it won't immediately come with answers, but it'll come tomorrow. And the exam itself, I will give you the details of and tell you whether we've resolved it to be like next Monday or what. Like, I'll still take any votes that I can take. But tomorrow I'll make a final decision and posting of exactly when this take-home midterm will be distributed and collected. It certainly, I mean, it won't be like tomorrow or something. It certainly won't be this week. But tomorrow you'll get the practice exam for it no matter what, and you'll get the details of what we resolved. And I have another class coming in now, strangely, I don't know if they're here yet, but I can certainly take any questions now because I know this has been, any questions at all? Dot product, cross product. Thank you very much. You guys are so, no, okay, fair enough. No, fair. Cool. Yeah, I don't know. Right, so I'm hanging either way. So if you don't have questions, it's been a pleasure. You know, God bless America. Electron bless America, by the way. I mean, you can believe in whatever, you know, whatever fantasy, crazy, electrons, unicorns, whatever, bless. But I must then have mentioned that at least what came out of the plague, like something good always comes out of it, right? What came out of the plague was Copernicus's invention of buttered toast, right? Yes, yes, yes. You guys are the best. Oh my God, you're gonna seriously, you're gonna rock this exam. Like, I'm glad you're not grading me on the exam. You're good. If you remember, you were totally gonna be fine on this exam. I wish I could teach you for real for more often. But okay, somebody got me. What? Ha! God, your chats, wow. I can't even imagine how funny they'd be if you thought I wasn't looking. Wow. Um, yes. And please feel free to go at any time. I'm just muttering because that's what I do to make sure the next people know I'm alive. But um, the Zen Buddhist said, as the Zen Buddhist said to the hot dog salesman, mutter, mutter, mutter. Yeah, look, the exam, that's hilarious. That is hilarious. Who are we kidding? The exam is about the plague, no matter how we phrase it. I mean, I mean, um, thank you guys. Yes, yes. And, uh, and you, I know, no, yeah, yeah, yeah. Okay. I'm going to be silent for a moment just to turn out here.